In this video, I introduce a latent plan transformer for trajectory abstraction. A plan of decision making is an abstraction lifted from the space of trajectories. Latent plan transformer is a plan generative model that uses a latent variable to collect a transformer-based trajectory generator and the final return predictor. As shown here, this is a latent variable z, this trajectory generator, and this return predictor. LPT is trained by using maximum likelihood estimate on trajectory return pairs without using stepwise reward. Given a variable length trajectory tau, a latent vector z represents trajectory tau. Y is the return of trajectory tau, and the joint distribution of tau and y is defined as p. Suppose the latent trajectory variable z can decouple the autoregressive policy and return estimation. LPT is written as here, which contains of three terms, namely p alpha, p beta, and p gamma, as shown here. This p alpha, this p beta, and this p gamma. Where theta is the model parameters, LPT approximates the data distribution p data using the marginal distribution p theta. Whereas the latent variable z is sampled from a neural network and z0 sampled from a normal distribution. This trajectory generator, which contains Gaussian transform and cross attention. Given a set of training examples, tau and y, LPT is trained using maximum likelihood estimate that maximizes the log likelihood L. Using chain rule, the joint probability of trajectory tau and final return y is expressed as here, where P0 is a normal distribution. Using Monte Carlo approximate, the gradient is computed by using this formulation. If theta alpha, theta beta, and theta gamma represent the expected gradients of L with respect to alpha, beta, gamma respectively, the gradients for each component is formulated as here. Estimating three expectations requires a Markov chain Monte Carlo sampling from the distribution p theta. Longevity dynamics is applied for MC sampling, iterating z for the target distribution pi as shown here, where k is the time step, s is the step size, and ek sampled from a normal distribution. Here, pi z is instantiated as a posterior distribution p theta. The gradient of log p theta is computed by using this formulation that consists of three terms, namely this prior, this return prediction, and this aggregating finite context subtrajectories. The posterior inference of z is the explicit process of optimizing a plan given his likelihood. P beta, modeled by transformer, can only account for sub-trajectories within a maximum length of k. The latent variable z serves as an abstraction that increases information from both the final return and the sub-trajectories using gradients. The sampling process starts by initializing z0, k0 from a normal distribution. In steps of longevity dynamics, approximate the posterior distribution, making learning algorithm approximate maximum likelihood estimate. During testing, LPT first enforces the latent variable Z0 given the desired return Y using Bayes' rule as shown here. The posterior sampling is achieved using Langevin dynamics, where the target distribution pi is replaced by posterior sampling p theta, and then MMC runs for the fixed number of steps. Sampling from p theta avoid back propagation through the trajectory generator b beta as shown here. The posterior sampling of p theta is explicit, which iteratively refines the latent plan Z, increasing its likelihood given the desired final return. Fix the head of the policy execution. The input Z serves as a plan. At each step, the agent consults this plan to generate action AT from this equation. Once a decision is made, the environment transition as t plus 1 from a transition function p emits the next state. The process iterates the sample of ST and AT until termination at the horizon. For more details, please check with these references. Thank you. Bye.